In this presentation, I'll discuss the relationships between effect size, sample size, and statistical power. We always want our studies to have high power, and sometimes it just doesn't happen because either the effect size is small or the sample size is small, or both are small. And so we really need to understand these issues in order to be able to maximize our statistical power. When we calculate significance tests, the p-value that you get from your significance test represents the probability that we achieve the results that we got by chance if the null hypothesis is true. It does not represent the probability of success if you do it again. And there are a lot of other things about the p-value that people believe which are just mistaken, not accurate perceptions of what the p-value tells us. There's only one thing that the p-value tells us, and that is the probability that we got the results as extreme as the ones that we did if in fact the null hypothesis is true. And of course the null hypothesis is that there's nothing going on, that there's no difference between a treatment and control group, or whatever it is that you're measuring. But what does this actually mean? What can we do with it? Well, in order to figure out, really what this means, we need to look at a typical table of hypothesis testing, and every stats textbook, every introductory stats textbook has a table something like this. This one is from the Welkowitz textbook, page 130. And so what we do is we line up our decisions with the true state of affairs. Of course, we never know what the true state is. So up at the top, we see the true state of the population. Now, if we knew what the true state of the population happens to be with respect to the treatment that we're studying, there would be no need to do the study because we'd already have the answer. So, a table like this is kind of deceptive in the sense that we don't actually have access to this information about the true state of the population, but we act as if we do. Now, there are two possible outcomes here in terms of the true state of the population. The first one is that HO, which stands for the null hypothesis, is actually true. In other words, there's no difference between treatment and control groups. And the other is that HO is actually false, which means that there is a treatment effect. So notice the directionality here of these statements. If HO is true, that's the same as saying that the null hypothesis is true, which is the same as saying that there is no treatment effect. Whereas on the right-hand side, if the HO is false, then the null hypothesis is false. In other words, the treatment does have an effect. But we need to have sufficient evidence that the null hypothesis is false before we can reject the null hypothesis, at least in terms of doing a statistical test. So let's focus first on the left-hand side of the table where HO is true. If that is the true state of affairs, if the null hypothesis is really true, if the treatment really has no effect, then the probability of committing a type 1 error is exactly equal to alpha, where alpha is defined by default, in psychological research anyway, as 0.05 or 5%. And that refers specifically to the tails of the probability distribution where the critical region is defined. So if the true state of affairs is that the null hypothesis is true, and if we accidentally get group differences between the treatment and control group, or whatever it is that we're testing, that makes it look like the groups are different. I mean, it can happen by chance. If you recall information about the central limit theorem, sometimes when you sample, the sample deviates substantially from the values of the population, and sometimes that deviation is simply a chance occurrence. So this type of error, type 1 error, this can happen exactly 5% of the time, at least based on statistical theory. Of course, we know that it happens more often than that because of publication bias, but that's a somewhat different issue, and I'll cover that elsewhere. So anyway, if we have sufficient evidence to reject the null hypothesis, and our decision is that we're going to reject the null hypothesis because our test result got to the critical region of the probability distribution, but in fact the treatment doesn't really work, that's a false positive, and that's what we're talking about here, type 1 error. Now, if the treatment really does not do anything and your decision is to retain the null hypothesis, then you've made a correct decision and everything is good. Of course, you're not happy because the treatment didn't work. Now let's focus on the right-hand side of the table, where it says the null hypothesis is actually false. In other words, this would be the situation where the treatment really does do something. Well, you need to be able to detect that treatment effect before you can reject the null hypothesis. So the correct decision here would be to reject the null hypothesis, and you can see the decision over here on the far left-hand side. But there's a probability involved in this, and that probability is 1 minus beta, where beta, as I wrote down here, is usually unknown, and it is only somewhat knowable. What you have to do in order to determine beta is first do a power analysis, and so this is by definition power. Power is your ability to reject the null hypothesis when it should be rejected. If you falsely reject the null hypothesis when it should not be rejected, then it's a type 1 error. But if you reject the null hypothesis when it should be rejected, then you've made a correct decision. The problem is, again, we don't know the true state of the population with respect to the treatment and control groups, so we never really know if we've made a type 1 error or if we made a correct decision. And it's kind of a problem, as you can imagine. Well, how do you get beta? Again, you have to do a power analysis, and in order to do a power analysis, you need to know the effect size. So I'll show you how to do that. Now, if the true state of affairs is that the null hypothesis is true, let me back up. If the true state of affairs is that the null hypothesis is false, see how confusing it gets with the terminology. So let's just say if the treatment really does work, but we are unable to detect the treatment effect, then we made a type 2 error, and that is equivalent to being blind to a treatment effect. And the probability of that happening is beta. So we don't want this to happen. We don't want either error to happen, type 1 or type 2. Type 1 is easy to compute. It's alpha, which is set at 0.05. But type 2 error, we don't know what beta is. In order to know beta, you have to do a power analysis and then extrapolate the beta. So let's take a look and see if we can figure out how to do this. Let's say we start with an independent samples t-test. You've got two groups. One is a treatment group, one is a control group. And we do the t-test, and we want to be able to reject the null hypothesis in order to show that the treatment really works. Let's say that we have 9 observations in each group. I'm doing a small sample here for illustrative purposes. Well, the first thing to do is we can locate the critical value that we need in order to reject the null hypothesis based on our t-test reaching that critical value. So we use a table like this in every introductory psychology statistics textbook, every basic undergraduate stats textbook, and the advanced ones too, have these tables in the back. This one is from the Walkowitz book. And the first thing that we want to do is we want to identify, well, which one of these columns do we use? I always just stick with two-tailed tests to keep it simple. Separately, differently in class, I'll talk about one-tailed tests, but not here. So just assume that we're using a two-tailed test of significance, and we're going to go with a 0.05 value. That is your alpha. That's alpha right there, and that's by default. We identify our degrees of freedom with 9 observations in each group and 2 groups. Then we have a total sample size of 18, but we lose 1 degree of freedom in each of those groups. So the degrees of freedom will be 16, and you locate that on the left-hand column over here. And then all that you do is you cross-index in order to get the critical value for your t-test, and any t-test that reaches that critical value or exceeds it will be evidence enough to reject the null hypothesis. If your test result is exactly t equals positive 2.12 or negative 2.12, then your p-value will be 0.05. So if you hit it right on the mark at 2.12, which is your critical value for t, then p will equal 0.05. And the further out, the further out into the tail, in either direction you go, so the upper tail or the lower tail, the further out your t-test goes, the more significant it gets. In other words, the p-value gets smaller.